All right. So we're doing P versus NP. I'm sure you've all at least heard those letters in that combination. And let's go about actually learning what that is. So the very first thing we want to talk about is the runtimes of problems, or as we'll come to see it, the complexity of problems. So we've learned throughout all of this that we have algorithms that have runtimes, and we can analyze those runtimes and discover how long it takes for those algorithms to operate. And now we want to ask the question, how do we say things about the problems that we're solving in terms of this runtime? And it's not immediately obvious because we have something like merge sort runs in n log n time, which is all well and good. But then the question is, like, how hard is the problem of sorting? Is it n log n no matter what? And then the answer to this question, or the way that we're going to try to approach this problem, is what's the runtime of the best sorting algorithm possible? And this is sort of a theoretical question. It's not exactly obvious to find that. And in fact, in a lot of cases, we don't know, and we kind of can't exactly know. Not that we can't, but we haven't yet. So instead of trying to find the best possible algorithm, we do that in some cases, but in general, we're not going to try to do that. We're going to compare problems with each other. And what we're going to find is that there will be similar properties between certain problems in their relationship with each other. And what we have is that those problems that have similar properties in terms of their difficulty will form what we call complexity classes. There's a little bit more nuance to the definition of these, but for now, we're just going to think of them as being problems that have similar kinds of difficulty. And we're going to get more specific too. So we'll talk about the first of our P versus NP, which is polynomial time algorithms. Polynomial time algorithms, or P, is a complexity class of all of the problems that are solvable in polynomial time. So what this means is that there exists some algorithm to solve each of the problems in P in O of n to the k for some k. So this means that like any formulation of the problem, we can solve it in polynomial time. So we know, like our example before sorting, we know that we have a polynomial time algorithm to sort. So that means that it is in P. So that problem is at least in P because we have an upper bound. So in general, we're going to sort of visually think about it this way. We have some input going to the algorithm, giving us an output. That's pretty obvious. And what we're going to think about is we want to find, one second, sorry. All right, so we want to show that for all inputs to some problem, our algorithm can produce the solution in some amount of time. And in polynomial, and for our polynomial complexity class, that is O of n to the k. So we're going to sort of think of this operation. This is the first of P versus NP, and now we're going to talk about the second one. So if we have all this, we will say that the problem that we are doing, like problem A that has these properties, is in P, and we notate it this way. So now we can talk about the second one. Actually, let's talk about some examples first. I forgot that includes some examples. So first, I'm going to ask if any of you can think of any problems that are in P. Not sorting, because I just did that one, but any other problems. I'm going to give you a minute to think about them. Throw them in chat. If you say them out loud, then that'd be good. I'll give you a coop buck. We were talking about coop bucks earlier. They're not worth anything. They don't do anything, but you can have them.
Searching.
Searching. That's a good point. So looking for paths, so finding a path, searching for a path is absolutely a polynomial time algorithm, or has a polynomial time algorithm, which means it is in P. So that's a good example. Here's a couple more. We have sorting, of course, I talked about. We can do it even in n. But I want to point out that n is in fact in polynomial time, even though it's not raised to any power. I mean, it's raised to 1, but yeah. We have min spanning tree. We have, the thing I want to point out here is we have Kruskal's, which runs in O of n log n. And in fact, though, we know that O of n log n, like, even though that's not explicitly a power of n, we do know that this is also O of n squared. You can also convert this to a power if you wanted. But so that one is also polynomial time. And basically every problem that we've approached in this class has been in P. So you can think through all of them and try to find, like, all the algorithms that we've done for the most part have had polynomial time algorithms to solve them. So in general, the problems that we see in this class are in P. All right. So I want to ask, though, if any of you can think of a problem that is not in P. And again, take a moment and try to think about all the problems, like even that we've seen, and see if there are any that you can come up with that are not in P. Or that you just expect aren't in P.
Finding a chess move.
Finding a chess move, that's a good one. Yeah, so if you're doing a full-blown search for like an optimal chess move, that is absolutely not in polynomial time. It is exponential pretty heavily. So in fact, we do know that that one's not in P. It's too hard. There's no algorithm, and we can actually prove that in that case. We can prove that there is no polynomial time algorithm to find the optimal chess move. Yeah.
The
So
halting problem.
Halting problem is a prime example of this. That, in fact, is a more interesting example than just not being in P. If you are interested in that sort of thing, the halting problem is a problem that essentially no computer can solve. That's no Turing machine can solve.
So what is it? What did you give as a good one for not in P but still computable?
Someone said a chess move, computing the optimal chess move.
Why chess move is not in P?
So if you want to find, or the only way that you can guarantee optimality for finding your chess move is to search the entire like search space of it, and it is exponentially growing. So the number of moves are
okay.
The size of your board is exponentially raised when you go to find an optimal move. So like a 4x4 chess board is very different than 8x8.
Okay, great, thank you.
Yeah. There's a lot of examples. There's a lot of examples of these sorts of things. We're going to talk about a few of them in a moment, but let's keep that in the back of our mind and think about that idea of which problems are in P and which ones aren't, and which ones can we know that they are and which ones they aren't. All right. So now we're going to get to actually talk about the second of the P versus NP, which is NP problems. So NP is slightly different. What it is the complexity class of all problems whose solutions can be checked in polynomial time. The name NP comes from non-deterministic polynomial time, which is called that for a reason, but in the context of like first learning this, it is better to think of it as being able to check the solution in polynomial time. So the sort of paradigm we can see here is that we are going to for all the problems, if we're given a solution, there exists some algorithm that can determine if that solution is valid, is a like actual correct solution in polynomial time. So you can try to think of some examples right now. I'll show you a little like graphic of how we think about this. So before we put our input into our solver and we get some output. And now what we're doing is we are putting it through something else, a checker, I call it, and it will give us either a 0 or a 1. Either it's valid or it's not valid. So now we have this sort of dynamic. And what we see when we're doing NP and we're seeing what problems are in NP, by our definition, the solver does not actually need to run in polynomial time. We can have some exponential runtime here to get to the solution, right? So we can take as long as we want to get our solution, but then when we go to check it, it will have to run in polynomial time. This is sort of the difference between P and NP is for P, we have to actually get a solution, and in NP, we just have to check a solution in polynomial time each. All right, so let's take a second to digest that. Does anyone have any questions about P or NP? Someone asked, is there any problem that is not in NP? There are, in fact. Actually, the example we just gave about the chess move is actually known to not be in NP. It's too hard. We can't check if it's the optimal move in polynomial time. The halting problem is also not in NP. So there are a lot of examples that are not in NP. There are a lot of different complexity classes above and below P and NP. But P and NP are particularly interesting for a reason that we're going to talk about later. All right. So that seems all good. All right. So let's move on to an example of NP problems. I'm going to give you a second again to think of any problems that might be in NP and see if you can come up with any.
Wouldn't it be heavily applicable to cryptography and signing?
It certainly is. It certainly is. We use certain NP problems to do certain things in cryptography. I'm probably not qualified to say much more than just that on it, but I do know about it, and it is interesting. So you're correct there. Yep. Anyone else want to come up with a specific problem?
Are Rubik's cubes in NP? Like really, really big ones as you make the size of the cube bigger than 3 by 3?
I think they would be, but I don't know for sure. That sounds like the sort of problem that is an NP though. These sorts of like branching problems where we have a bunch of different moves tend to be problems that we think of as being an NP. And Ben says nanograms are an NP. I don't actually know what nanograms are, so I'm going to take his word for it, but not tell you that that's true. All right. So one thing that we might notice immediately about NP and problems that are NP is that all of P is actually in NP. This is something that might feel slightly counterintuitive from the way that I've described these things. But if we think about the definitions, right, we have said that in P, right, we will have a solver that runs in polynomial time. So we know that this will run in polynomial time to get some solution. And what we want for NP is we want some checker that will be able to tell us if we got the correct solution. And we need that to run in polynomial time. And then the question becomes, like, how do we use this solver that we know exists to make a checker? And it is actually very simple. We just put in our input into the solver, we get an output, and then we check if it is the same as the input that we were given. And if it was, then we say that's good. So there are ways that we can formulate the problems to get around having like multiple solutions and all of this. So we can just simply check that these are the same. And we can do all of that in polynomial time. So in fact, our checker can run in polynomial time. So that's very nice for us. And it is sort of a conceptual thing that you should try to understand is that P is encapsulated by NP. All right. So one way, I guess I'll give you another example actually first. So Sudoku is a sort of prime example for this sort of thing. It's similar to the Rubik's Cube problem that you're talking about, but it's a little bit more like direct. So Sudoku is, if you don't know, we have to use rules where no numbers can repeat on a horizontal or vertical line or inside of these 3 by 3 boxes. I didn't cut them very well, but that's a Sudoku problem. You don't really need to know it for this. And I want you to try to answer this. So how long would it take to solve a Sudoku problem naively? So just think about that problem for a second and throw out a guess. You don't need to think about it too hard.
So each cell can have, what, 9 different options?
Yep.
And there's, if the board is like n by n, right? There's n by n different cells. So that would be like 9 to the power of n by n total different ways you could fill that in.
Yeah, we actually call it n squared by n squared board. That's just the way it's formulated when people talk about it. It's not too important, but you are right. And I really say that just as a, like, without going too in depth of what it is, I just say that it is exponential. So I say n 9 to the n, but it really has a more formal definition if you want to look into it. But naively, we are essentially just checking all the different options that we have. And in fact, if we, like, or at least people who have tried to come up with better algorithms here to do it in non-exponential time have failed. So we say that is something exponential. I'm sure there's something better than 9 to the n, but there is nothing that is polynomial that we know of. So then the question is, if I give you the solution to this problem, how long does it take to verify? And you can throw out another guess there, although you might.
Well, you just need to check each row, column, and square. So that should be linear time.
Yeah, it is very short to do, and I think there is, in fact, it is actually polynomial, but it is very small, and I'm sure there is very fast ways that you can do it. Like, I think it always ends up being polynomial though. All right, so this is like a sort of a prime example where we have a problem that seems insanely difficult to actually solve, but is very easy to check, and this is sort of the nature of NP problems. And when we think about NP problems, this is sort of what we expect to see. and the reason that we classify it on its own, basically. And this is pretty insane that there's this much of a difference. You can imagine for n 100, these are very different numbers. All right. So because of this property here, where we have that it is checked, so we only need the second property, then we know that it is in NP. And we actually know one other thing about this problem. We actually know that Sudoku is in a class that we call NP hard, which is something that we're about to talk about. So what is NP hard? That's a good question. So a problem is considered NP hard if it is as hard or harder than every problem in NP. So the immediate question is, what does hard or harder mean in here? And we'll get there. One visualization that I kind of want you to have, though, is that we have our complexity classes like this. This is similar to a hierarchical model of complexity. If you ever take 501 with Immerman, he talks about this quite a bit in quite depth. So we can sort of think as like having the harder problems be like above the easier problems. So we have the NP problems are above the P problems are above the linear problems. And we can say that all the problems in P are in NP, but we don't necessarily have it the other way around because we have that all of NP is harder than P. All right. So all of P is inside of NP. All right. So how we can sort of think of this is that all the complexity classes that are lower in our hierarchy are contained by the ones above it. So all linear problems, all things in L, are also in P. So we can sort of think that all problems in P are in NP. And this is sort of a paradigm of how to think about this. And now we have our NP hard. And NP hard sort of sits, it is inside of NP, but it is sort of the pinnacle of it. And this is a sort of a different thing where we have that NP hard, like problems that are in P are not necessarily in NP, but NP hard is a special section of NP that is harder than the rest of them. And we actually, I should specify that NP hard does not necessarily mean that they are in NP. So that's a distinction that I didn't make very well, but I do want to make now. That NP hard problems just have to be above NP. They just have to be harder than NP. And there's a classification for that. So basically everything in the hierarchy that is above NP, that includes some amount of NP, is considered NP hard. All right. So how do we compare things? So we talked about how we don't really know what harder and whatnot mean in this context. And what we're going to do is we're going to define a way to classify that. So what we're going to talk about are reductions. So a reduction is defined as such. So we have a problem A and a problem B, and we say that A is reducible to B, and this is the notation for that, is reducible to B in polynomial time. And we say that that is the case if we have some function such that for every instance of the problem A, we can convert that problem A into a problem using our function that is in B. All right, so I know this notation is a little bit uninformative and a little bit doesn't really help your intuition about this. So I'll write it out a little bit. So we must be able to convert, and this is in polynomial time, that's where this little p is from a problem of type A to one of type B. And we also need to preserve a certain property. We need to know that the converted problem, when solved as a B-type problem, will give us the same solution as if it were an A-type problem. So this is an important property because it means that we can essentially map our solutions from, map our problems from A into B-type problems, and then just solve them there. So you can sort of get some intuition about why this is a good way to think about these reductions and to order our things. So we can say if we can solve it as a B-type problem and we can get there in polynomial time, then we know that A must be as easy or easier than B. So you can sort of try to convince yourself of that intuition, but we're going to give some more examples about it. So try to understand this. Write down this if you are interested in this sort of topic and think about it. Later on, you might want to use this to think about P and NP. All right. So let's talk about an example. So first, let's see the knapsack problem. So you probably all remember the knapsack problem. I'm going to try to use problems that we've already seen in the class first, so I can give you an idea. So in the knapsack problem, it has our weights and our values, right? If you remember it all. A slight refresher to it, we have our weights W1 through Wn and values V1 through Vn. And we are trying to choose items, which each have a weight and a value. And we want to choose values that do not, or we want to choose items such that the weight, the total weight between them, does not exceed some upper threshold, some weight limit W. And what we want to do is we want to choose the items that will maximize our value. So we want to pick the most valuable items without going over our weight. That's the knapsack problem. I'm sure you all recall. So can anyone think of a problem that this is very similar to, that we've already seen? I'm going to give it a couple of seconds in case someone can come up with something.
The rod cutting problem?
That's a good call. That's a good call. In fact, that's the one that I chose for this, and it is very similar. So let's talk about the rod cutting problem. You get a coop buck, Connor, so congrats. All right, so the rod cutting problem is as follows. We have a rod, and we have a set of sizes and costs. And what we want to do is we want to take our rod of size S, and we want to break it up into different sized rods. And what we want to do is maximize, or we want to maximize our cost by splitting it into smaller sections. So that is the task. I'm sure you all remember. I won't dwell on that. So now I want to give you a second to think about the idea of converting the knapsack problem into the rod cutting problem. So take a moment and maybe write down some stuff and think about it. I don't think I actually give you an opportunity here quite yet. Yeah, so give it a moment and try to think about how you might do it. And if you come up with something, feel free to put it in chat or shout. Don't feel too bad if you can't come up with something, by the way. This is your first time seeing reductions, so don't feel bad about it. All right, I think that's about enough time for you guys to at least have thought about it. All right, so let's look at this. So what we want to do is we want to do this reduction, all right? And remember, we're doing the reduction from knapsack to rod cutting. That's the format. So try to remember that. That's something that gets confusing for people inevitably when you are working with reductions. So what we want to do is we want to take a knapsack problem, right? And we want to convert it into a rod cutting problem. So we want to first look at these different tables and we want to convert them. And what we see in this case is actually that we can just convert them essentially one-to-one. If we think about it, we have some maximum weight that we are splitting up into different weights, and we are summing them up like that. In the rod cutting problem, we have a maximum rod size, and we are splitting it up into different rod sizes, and we are maximizing. So both of these problems are formulated very similarly. We can see we have our max weight, and we just convert that to a rod of size S. So for the most part, we essentially just rename our tables and rename our max weight variable into the rod size. There is, however, one thing that we need to deal with in this case, and if anyone can think of it, that'd be cool.
Well, in the rod cutting problem, we divide it into a number of rods that are, the sum is exactly equal to the length of the rod. In the max weight problem, it has to be less than or equal to the weight.
That's exactly right. And can you think of a way that we could modify our translation here to accommodate for that? There's something very simple that
we can make it a fractional knapsack problem, but that would be sort of,
So that wouldn't work exactly. There are some problems in doing the one-to-one there. So in both of these, we know that the weight and the size are some integer, right? Both of these are integer-related problems like that. So what we can actually do is just add onto this table one more entry, which is size 1, cost 0. So essentially what that does is we will have some amount of unfilled space, like in an optimal solution to our weight problem, into our knapsack problem, we might have some unused weight. And to accommodate for that, we essentially just fill it with cost 0. So that's what we do for our rod cutting. I hope, does that work? Everyone feel good about that?
Yeah.
All right. Hopefully this idea of reductions has landed, because we're going to get a bit more complicated about it now. So let that sink in for a second. This. Nice. I felt like it felt like it sunk. I feel it. All right. So now we're going to talk about a different problem. This is a problem you've never seen before, most likely. Maybe some of you have. It's called 3-sat. So the problem is 3 satisfiability. So it's 3-sat problem. And the problem is designed where we have a number of clauses. And we define those clauses as a set of variables ORed together for 3 variables. So this is 3-sat, which is why we have 3 variables here, right? So this is a clause. And then when we're taking our input to our 3-sat is going to be n clauses all anded together. And something I want to note, because I use like 1, 2, 3 here, is that each of our clauses can have any mixture of variables. We'll have some number of variables, at most 3n, but we'll have some number of variables, and we're allowed to mix them however we'd like. So, this could have been 3, 1, 2, this could be whatever. And we can have all the way up to like the last one can be in our first clause. It doesn't matter. We have some mixture of 3 variables in each of our clauses, and we and them together. And then the problem is finding out if there is a way that we can assign these variables either true or false, such that this entire statement is true. So the problem is to see if there is any, not to say what it is, but just say if there is any. It's pretty easy to think about how if you are able to say there is any, you can very likely find a solution. But for now, we're just thinking about, is there any solution to this problem? And that is what the problem is. That's what the 3-sat problem is. And this assignment of variables in a way that would cause this entire statement to be true is called a satisfying assignment. So this sort of problem where we are only getting a yes or no out of it, I know I've said that that's what we're doing in NP problems generally. That is called that's called a decision problem, and it's a big class of class of problems. And in fact, we convert a lot of problems into decision problems because it allows us to do.
Maybe you just want to mention that the variables can be in the positive form or in the negative form.
Yeah,
I would want to have false.
Worth mentioning as well, yes. So they can be negatives. For example, if we had, this could be not x1 and this can be x1, and then we are not allowed to, we can have only pick one of them. So if we had 1, 2, 3 and not 1, not 2, or not 3, then obviously we have no solution to it. So that's important to note. That's why it's an interesting problem, really. Otherwise, we just set them all to true. Yeah, good point. All right. So keeping this in our mind, let's talk about this problem a little bit. So first off, I want to ask, just use your intuition or use a little bit of logic to determine, do you think 3-sat is in NP? Connor's nodding, so I'll take that as a yes from him. Yeah?
I think so.
I think
Because we only have to check whether or not is each case of the clause is like true or not. So it should be taken.
Yeah. Essentially, all we are doing is resolving this logical statement, and that is absolutely possible to do in polynomial time. So it is an NP, all right? And I'll ask you just to think about this. How long do you think it takes to solve? Like if you used a naive solution, how long might it take?
Wait, hold on a sec. You said that something's an NP if we're given a solution and we can check if that solution is correct in polynomial time.
Yep.
But here, I thought you said that like the solution that we're given isn't necessarily a value for each of these Boolean variables. It's just a yes or no. This is satisfiable or this is not satisfiable, right?
Yeah, yeah. So yeah, if we're given a valid assignment of them, then we can check in.
Right. So yeah, but I'm just saying, like, if you only told us like a yes or no, I feel like this.
No, that's a good thing to point out, that I was not clear about that. So it's more than just being given a valid solution to the problem. It is being given like the formulation of the answer of the solution. So
Okay.
you are given actually that, and you can
Okay,
generate
yes.
problems to
Of
make
the
that.
yes solution. So if the answer is yes, you want to have a positive one. If the answer is no, you don't have to say, because you don't have a solution that proves to you that nothing is possible. So you really, the answer, the polynomial time is only if the answer is yes.
Okay.
Okay, so we'll say that it takes quite a while to solve naively. It takes exponential time. Again, there is no known way to solve this in polynomial time. Not to say there doesn't exist one, just we don't know if there does, and we haven't found one. And it only takes polynomial time to check. So it is in NP, and it is not in P for all we know. So that's how we think about this problem. And in fact, so we know it's in NP, and we actually know that it is NP hard. This is one of the first and most fundamental problems that we actually know is in NP hard. You can imagine it's a little bit tricky to prove that something is NP hard. From what I've described so far, you need to prove that it is harder than every single other problem. But we can talk about that a little bit now. All right. So let's talk about NP hard again. So we gave sort of an informal definition at the beginning. We said that that A was an NP hard if it was harder than every other problem. But then we talked about how we can define what harder is as reduction, and now we can give it a slightly more formal definition. So we say that A is an NP hard is exactly the same as saying for all problems in NP, which we label as B, B can be reduced to A. So that is the more formal definition. It's exactly the same thing as what we were talking about before, but it's written out a little bit more explicitly now. So every problem in NP has to be reducible to A for A to be NP hard. That is what NP hard is defined as. So it's the same definition, it's just formal. I do want to point out, like I said before, that NP hard is not necessarily an NP, and this does hold for this reduction. So if we had a problem that was exponential time, or exponential in the exponential complexity class, then we could show that every NP problem is still reducible to it. So we do have an interesting thing here. All right, or not necessarily in exponential time, but if we had one that was harder than NP, then we could show that all of them were reducible to it. All right, so 3-sat is NP hard, and I'm going to ask the question, can there be more than one NP hard question? What does your intuition say?
Do you mind to repeat the question?
Yeah, so the question is, we have now an NP hard problem. We've seen one earlier, so I kind of gave away the answer here, but just intuitively, does it feel like we could have multiple NP hard problems?
I guess yes, it does.
It does feel that way, doesn't it? So the thing that makes this possible is that we actually have problems. So we have an NP hard problem in 3-sat. We have an NP hard problem in Sudoku, like I told you. So if they are both harder than every other problem in NP, and I in fact told you that they are both in NP, then they must be harder or as hard as each other. And what we actually get from that is that all of these NP hard problems that are in NP are in fact equally difficult. So we would have this reduction going both directions for those cases. That's just an interesting point I want to make. It's not quite as important for this next bit, but I do want to point it out. All right. So sort of just think about the significance of statements like those in the back of your mind. Let it just simmer in your subconscious while we talk about the next bit. We're going to do another example of reduction. All right. Oh, man. All right. So the 3 coloring problem, which you may have heard of, is a problem where we take a graph, right? So we're going to take a graph like so, and then what we want to do is we want to find whether or not there is a way that we could color these nodes using just 3 colors such that no color or no neighbors have the same color. So I asked, like, what's a solution for up here? You don't need to tell me, I'll just show you. Something like this would work. If we had the 3 colors, purple, blue, and green, we could color it like so, and you see that that is totally viable. All right, cool. So hopefully that problem makes sense. Does everyone understand? I'll go back to some of the questions because Hava answered them. Yeah, they were just variables. The x5 and x8 were just other variables. All right, cool. All right, so now for this one we have true, and now we want to do a reduction. So we're going to want to reduce 3sat to 3 coloring. So if we are able to do that, that means that 3 coloring is harder or as hard as an NP hard problem as 3sat. So let's see. So this is going to be a little bit harder of a reduction. Earlier we were able to just map them 1-to-1, but we want to come up with a like way that we are able to convert a 3sat problem into a 3 coloring problem formulaically. All right. So I'm going to show you this definition again just to remind you slightly. Remember, that means that we have some function, there exists some function, so that we can convert any element in A, which is going to be in 3sat, into a problem that is in B, which is 3 coloring. So we're able to take problems in 3sat and translate it into problems in 3 coloring, and we can do that for every problem in 3sat. And then we can use our solutions in our new domain in B to get our solutions to A. So we can essentially use what we know about 3 coloring to solve 3sat problems. That's essentially the idea. All right. So this is same as the definition before, just writing it out for you. And we have to be reminded that we need, like in this conversion, we need the solutions to still be the same or to be translated in the same way. So we need to keep track of that, and we need to make sure that we can convert the entire input of the problem, or the entire like structure of the problem. All right. So they're both decision problems. We have the 3sat and we have the graph coloring, and they both tell us yes or no, whether we can or whether we cannot. So we know that the solutions will be binary, so we don't need to worry about that too much. We just need to make sure that they are correct. All right. So I'm going to give you a little bit of time to think about this one, because this one's a very interesting one. I actually I made up a solution of how to reduce this for this lecture, and I can tell you it's a pretty satisfying problem when you get it. I'm going to give you some time to do it just to go through the motions of trying to figure it out. So we have these clauses all ANDed together, and we want to convert it into a coloring problem. All right. So we want to do that in polynomial time as well. So I'm genuinely going to give you guys like 5 minutes, maybe a little bit more, to think about this, and just write it down and try to see how you might want to convert it. To ease your minds a little bit. Okay. Hava says this is too hard. I think that's fair. I think that's fair. I'll give you pieces to it, but do try to think about it. All right, man. All right. So I forgot the animations here, but we are assigning 2 specific colors. We're assigning green to mean true, and we're assigning red to mean false. Are the first things that we're going to do. Just because we have this binary, it's a nice little mechanism where, because we have this binary relationship in 3sat, we want to have that in our coloring in some way. And what we're going to do is, for each of our variables, so for the variable x1, we're going to create 2 nodes, one of which is x1 and one of which is not x1. And what we're going to do is we're going to connect them both to some other node, A, I named it, which has the 3rd color. So it's not the true color, not the false color, it's the other color. That means each of these could only ever be defined as true or as false, one of these colors. And if one is true, then the other must be false. So now we have this sort of relationship where we can say for each of these variables, if we have this for each of our variables, which I show here, then we know that we will be able to say one is true and one is false. Right? So if this one is true, for example, that means that xn is not true. So try to make sure you understand that relationship there. So you can try to piece together. I'm going to again go a little bit slow so that you guys can like try to think about it, because I think it's an interesting problem. and try to think about how maybe you would use this to create the coloring. All right. So after we have these variables, the next question, oh man, I missed the animation at the end. So the next question becomes, how do we actually do our clauses? So we're going to first create an OR gate. So we have this like before. You can ignore this for now. So we have our variables like before, and we're going to take two of our variables and we want to OR them together. What we're going to do is we are going to connect them both to A. So these are just variables that were from here, right? They're connected to A like they were defined. You see this is xv and this is xu, so they're two separate variables. In fact, not xu. And what we're going to do is we're going to create nodes coming off of each of these, right? So those won't be able to have the same colors as each of these. And then we're going to connect them together so they can't have the same colors as each other. And then we're going to, so we see if we have them both be red, right? Then we know that this one could only ever be purple or green, and same with this one. So one will be purple, one will be green. We know that from how we've designed this problem. So I said this one can be purple or green, and this one also can be purple or green, and that's it because it's connected to red. So like I said, one will be purple, one will be green. And now what we're going to do is we're going to connect them together. And the question is, what color must this be if both of these are red? Red. Thank you, Alex. Yeah. So this one must be red if each of these are red. And what I nicely didn't have an animation for is if we add a node that we have as a baseline false, so we just color it red at the beginning and connect it here, then we will only ever be able to color this. It will only ever be colorable if one of these is not red. And since it can't be purple, it must be green. So what we actually see as this node right here will take on an OR gate. All right, okay, maybe it was a bit hard, but yeah, so you have to create an OR gate out of our colorings, which we get here. If we connect it to here, then we know that this will operate as an OR gate for one of these being true. All right, nice. So like I said before, this one will take on the OR. Yeah, okay. So like I said, it's only colorable if one of these is green. So try to rationalize this to yourself. I know I'm taking a lot of time to just like repeat this a little bit, but I want you to try to understand why that is. Do we have the first MPH problem from which we started the reductions? I don't know exactly what we're talking or what you're asking about. I'll keep going for now. Yeah.
For example, the first one you prove not by reduction. The first one you prove by being NP hard.
Sudoku?
Whichever. I mean, you have to start with something that you know that is NP hard, or else you cannot do reductions.
Yeah,
we're do reductions, but you must know that one of them is NP hard, or that all programming NP hard can be reduced to.
Yeah. I was going to talk about that a little bit further on, but I sort of just gave them that it was NP hard. So I guess I can talk about that right now. So as we've described, we had that 3-sat was NP hard. I'll talk about it very briefly. So we know that 3-sat is NP hard because I gave that to you. What we have to do is, find a problem that is NP hard. Actually, I have this later on that is a more appropriate time, I think, to talk about it. I think
No, you can wait. That's okay. It's not
okay, I'll finish this proof first. All right. So we have our OR gate now, and now what we want to do is we want to think about clauses. So a common way for us to do these sorts of reductions, specifically with 3-sat, there's a lot of reductions from 3-sat, is we want to have sort of mechanisms that do different things. So we want to be able to create a mechanism in the structure of the problem that we're reducing to that has variables that can be binary. And then we also want to convert the clauses so that we can solve those clauses. And then by solving the entire set of clauses, we get our actual correct solution. So let's look at an example of a clause, right? So we have our variables, right? I'll use a more specific example here. We have 1, 2, and 3, right? Which are these 3 right here. And we will create our first OR gate. So this is the same thing we saw before. So we have x1 here and not x2 here. We will just draw the connections between them, right? So this is like connected like, or these are these, right? If you can imagine. I just don't want to make this too complicated. So these are this will OR through it. So if one of these is green, then this whole entire thing will be green. Can be green or can be red. So we're going to introduce our new variable, x3 here. And what we know is that OR is commutative, so we can actually have an OR between the output of this OR gate and this one new node that we're adding. So we're going to do it similarly to how we did an OR gate here, and we will actually end up here with an OR between all three variables. Now there is something kind of amiss with this OR right here. So what values could this OR take, if you want to take a second to try to think about that? So if we have like this one right here, we'll be able to take on the values of either of these colors. So if there is a red and a green, then this one could be red or green. If there are two greens, it could just be a green. And if there are two reds, it can just be a red. All right. So we have another one of those gates going here, but we lose one property when we go a second OR. I'm going to ask these as sort of hypotheticals. I know they are pretty hard, and I don't expect you to be able to solve them on the fly necessarily. If someone has a clever solution, though, I do want to hear it, but I'll keep going with the proof. All right. So what we actually see is that this one could take on the value of purple. So if we have like a green here, then this one can only be green. And we have red here, then this one can only be red or purple. So it could be red, and then we have a purple here, hypothetically. And we don't want to be able to have a purple here. We want it to only ever be binary. We only ever want it to be true or false. So what we have to do is we have to connect it to false, firstly, so that we have this same property with the other OR. And then we also have to connect it to our grounding purple color. So if we do this, then we know that it can only ever be green. So if we want to have a valid coloring, this one can only ever be green, and it can only ever be green if one of these three is green. Does that make sense? All right, I'm seeing a nod there. So essentially, this is the entire proof for the reduction. We do have to prove that we can do this in polynomial time. I'm going to ask that you just trust me on that so that we can get to a little bit more material, but we can do this reduction in polynomial time, and we can see that for any input, we can design this structure for each of these clauses, and we just need to have all the clauses all together. We don't need to actually create any AND gates, because it was sort of implicitly there, because we need to be able to color all of it all at once. So as long as we create one of these little mechanisms for each of the clauses and one of these little mechanisms for each of the variables, we actually know that this coloring is only ever possible if every single one of these is satisfiable. So this problem ends up being exactly reduced with correctly. So we just need this formulation, and this is sort of a indicator of the sorts of tricks that we use in reduction a lot of the time. They aren't as straightforward as the first example made it. Do we need another horizontal line between these two? I assume I may have missed that. 1 second. So if these are all red, for example. I don't think we actually do. We may actually need it though. We probably do, but I won't dwell on it too much. This is basically the structure. All right, cool. All right, so like I said before, it will only be colorable if at least one of these variables is true, and we can extrapolate that so that we know that there is only a satisfiable, there is only a coloring solution if the problem is satisfiable. They are one-to-one like that. All right, so that is a proper reduction. So now we get some takeaways from that. So we know now that 3-sat is reducible to 3 coloring. All right. We also know that 3-sat is NP hard. And I want to ask, can we deduce anything from those two statements?
So that means that 3 coloring is just as hard as NP hard problems, or it could be harder than them?
So it could be harder. We'll talk about that in a second. What we know from it is that 3 coloring is NP hard. And I want to take a moment to extrapolate out from that. So if we have our NP hard problem, which must be harder than all of these other problems, then we know that, so if we know that that one is harder than all NP problems, and this one is harder than that one, then we know that this is also harder than all of the NP problems still. So that means it's NP hard by definition. The thing here that you sort of need to accept, but you can rationalize very easily, is that this reduction operation is transitive. So if we have multiple together, then it does transition between them. You can think it's very easy to prove that actually. You can just do multiple of these polynomial time reductions between them, and you can show that it is transitive because there is some finite number of these, or some set number of these, right? So there is one thing we don't actually know from these two statements, and Simon was sort of indicating that. So the thing we don't know is 3 coloring in NP? So we know that it's harder than everything in NP, at least, harder or as hard as everything in NP. We don't actually know if it is in NP. Anyone want to give a guess?
So if we're like taking 3 coloring as an NP problem, right? We're looking to see like how difficult it is to solve that problem as a function of its size. So here, is the size like considered 3 because we're using 3 colors, or is it like the number of nodes in our graph, or the number of edges in our graph? Like what are we looking at to scale here?
So you can think of it as the number of vertices and edges. So like you can think of them as separate variables, sort of, but like think of it in terms of like the number of edges is the largest number that there is in terms of there. So by the number of edges, like if we have some number of edges, how long would it take? If we have n edges, how long would it take for us to verify 3 coloring? I know that one is not super precise. There are more precise formulations of like what you're asking, and I probably so I think my answer is satisfactory, but also there are better answers out there. But I would say look them up, and you can see sort of how we formulate these problems more formally. Okay. But the answer for how long it takes to check is we essentially can do it in linear time. We just need to check that each of the vertices don't have a neighbor that has. We check by each edge whether each node has the same on each end of each edge, and then we just need to check each of them that way. So it is just going through each of the edges. So it is very easy to verify. So we actually do know it's in NP. And we know something that I have not talked about yet, but we know something kind of interesting, which is if we have a problem that is NP hard and is in NP, then we actually have a specific NP, or we have a specific complexity class for it, which is NP complete. So a problem is NP complete if it is both NP hard and also in NP. I think now would probably be a good time to tackle the question that Hava raised earlier, which is, we can find that something else is NP hard, like we can find that 3 coloring is NP hard by doing this reduction. But the question arises, if we are unable to do a reduction, if we don't know any problems are NP hard, how do we prove that a problem is NP hard? And this was one of the fundamental things, and the proof for it was essentially to formulate a generic satisfiability problem. There was a circuit satisfiability, and the proof essentially demonstrated that any problem that we could check in polynomial time, we could formulate as a circuit problem, circuit satisfiability problem. And I would recommend that you look up that proof. It's a pretty interesting one. I think it is probably slightly outside the scope of what I want to talk about right now, but also is fundamental to how we understand the relationships of NP hard problems and NP. So it is a very interesting thing and very important thing. I just didn't prepare very much on it, and it is a slightly more involved proof. All right. So these are the conclusions we can take away from it. All right. So now we get to the actual meat of the issue, which is this problem. It's the name of the lecture, all of this, P versus NP. So this is a fundamentally unanswered question. This is something that is very interesting to think about. Do we know if P is the same as NP? Do we know they're the same, or do we know that they're different? Like, are they different, or are they exactly the same? Are there any problems in NP that cannot be solved in polynomial time? And the interesting part of this problem might not, like, all of that might not exactly interest you. The interesting part for you may be that no one has an answer. No one has a proved, like, agreed upon answer. So we don't know at present whether a problem that can be checked easily can be solved easily. This is sort of the relationship that we don't fully understand. And that's, very interesting. If there is a hard problem, but we're able to check our solution very easily, can it actually be solved quickly and we just don't know it yet? Or is there something fundamentally different about that, about the difficulty of solving and verifying a solution? And it's interesting. There are a lot of aspects of, like, computer science and algorithms and, like, much more theoretical findings that, like, rely on understanding this that we can't verify yet, about understanding this relationship. There's a lot of interesting things that are related to that. So, like, fundamentally, if we understand this, if we get a solution one way or the other, it will kind of fundamentally change how we see complexity, or at least will, verify some things and change other things. So it's a very big problem. It's a, this is one of these things that, kind of shatter your worldview, your, the curtain that everything is already solved and there's nothing for you to do, and everything that is fundamentally interesting in computer science, math, and all of this has already been done by someone. There's some brilliant mathematician 500 years ago already proved this. And it can kind of shatter that view a little bit, because this is very important, very fundamental, and we don't know. In fact, this is one of the millennium problems. If some of you don't know what they are, probably a lot of you don't know what they are. They are a collection of very important problems, mathematical problems, that are hosted or are being posed by the Clay Institute for Mathematics, I think. And if you're able to solve any of the millennium problems, get a proper solution that is agreed upon, there is $1 million prize. So to really hit home the importance of this problem and the interest in this problem, what happens is P equals NP. Okay. Yeah, if you have more to say about that, Hava, I'd be happy to hear about it. I know you do more than this. What happens if P equals NP? No, well, a lot of things do happen. I mean, it means then that, like, actually, if you want to speak about this a little bit, I think you're probably more qualified to talk about this than I am. I know, yeah, $1 million is good. Yeah. So I do want to try to talk about something nice. So I want to talk about how we might go about solving this. And this is sort of an interesting place where a lot of you probably, don't feel like you understand this problem well enough to even approach it or even look at it. But I think it is a worthwhile thing to try to do. And in fact, all of the things that I've taught you here are basically the only tools that you need to prove this, to try to prove this at least. So let's talk about how we might want to do that. All right. So if we want to prove that P equals NP, we can go about it in a pretty simple way. So in fact, this is the simpler of the two conclusions for you to try to prove. So if you think somewhere in your heart that this is true, you can go about trying to prove it in a pretty simple way, in a way that one of you could definitely approach. Bailey is correct about that. Yeah, that means that we could do that hypothetically, which is interesting because there are problems like Sudoku that seem out of reach, and these sort of branching problems, even things, not exactly chess, but things like chess with these branching moves, could be solvable in polynomial time, which sort of changes how we think about our modern solutions. And we think that there are probably much, much better solutions or better ways to formulate these problems. It would open up huge areas of research, and it is it's big and important. And some people have even written about, if we assume this, what can we do? And if we assume the opposite, what can we do? And it's pretty interesting. All right. So again, this is a simpler one to prove. And here's how we would go about it. So say we have some problem A that is NP complete. All right, so we say we have some problem that is NP complete, or NP hard even, but we'll say it's NP complete. And we have some problem B that is in polynomial time. So we have two problems here. And the question is, if we have, like, how could we use these two problems that are in these different complexity classes, using just what we've seen today, how could we prove that P equals NP? I'll give you a moment to think about it. So we have a problem that is NP complete, so it is harder or as hard as every problem in NP, and it's also an NP, which means that every problem in NP can be reduced to it, right? So we have that reduction. And now we have something in polynomial time, which we consider to be lower, but is a different problem, is in P. And how could we try, at least, to prove that P equals NP? As a hint, we do know that, yeah, William?
Well, wouldn't we just need to prove that that one problem A is solvable in polynomial time?
Yes, and like, if we proved that, like, we could just prove that A is solvable in polynomial time, then good. And more explicitly, and probably a slightly better approach is Michael's, which is if A reduces to B, right, then that means that A is easier or as easy as B, which, because of the transitive property of like this reduction, means that every problem in NP can now be reduced to this one problem in P, which then means that NP, like as a class, is as easy or easier than P, right? So now we have changed the hierarchy, so now P is at least, is higher than NP. And now what we get from that, because we know that P is bigger than NP, right? P is as big or bigger than NP, or as hard or harder. And we also know that NP is harder or as hard as P. We know they're in fact equal. So we get that nice little collapse of all of our hierarchy if we get this one reduction. So all we would need to do, if you want to try to approach this problem, P equals NP, all you would need to do is find some problem B such that there is an NP complete problem that reduces to it. That's all you would need to do. So you could try coming up with one. It could be as high a polynomial as you'd like. It could be n to the million to solve it. And as long though as it's polynomial and you show that NP complete can be an NP complete problem can be reduced to your new problem, then you have the solution. So I recommend for all of you, it seems like this is such an easy thing to do, right? I described in a single lecture how to do reductions, what each of these things are, and this is such a simple thing to try to prove, and yet no one has been able to prove that P equals NP for years, for decades. So it's interesting to see it, but it's worth trying, I think. Maybe you'll hit on something interesting. It's commonplace for a lot of us, a lot of students, is what I was saying, for us to think that we are unworthy to attack these problems. So I'll talk about that in a second. But I do think, even with your inexperience, you can come up with some very creative solutions to this, and it is definitely worth doing. It's worth thinking about, and sometimes you will actually come up with an interesting solution, even as students who feel like they don't know that much. So I'd say definitely try it. What Hava asks is, how would we prove the reverse, that P is not in NP? So we kind of talked about that a little bit. So some things that we could do is we could prove that every single NP complete problem is harder than every single polynomial problem. So we just need to pick some NP complete problem and show that it is harder than every polynomial problem, and those polynomial problems, then that it can't be reduced to those polynomial problems. So it's harder than these polynomial problems, and these polynomial problems are not as hard as that problem. If we do that for one NP-complete problem, then we know that P is not equal to NP. We could also create a P-hard problem or a P-complete problem that is harder or as hard as every in P, and then show that we have a one-directional reduction between that new P-complete problem and an NP-complete problem. That would at least show that there are some problems, at least our NP-complete problems, that are not in P. So we could do that, and that would show that P is not equal to NP, or the first thing I said would also prove that. They are slightly harder, and they are more conceptually complicated. I mean, you have all the things you need to come up with those solutions as well. So if you want to approach either side, you can. It's just that this one is a simple reduction. So as long as you are able to do a reduction, you're able to approach this. So we're nearing the end of our time. And I want to, this is a little bit of our cap off with a P and NP, but I want to show you one more problem. And I just want you to think about it, and we'll see if we can come up with a solution in the remaining time. All right, so we have a new problem here. I'm going to give you two new problems, and we're going to do a reduction. So we have independent set problem. What this is we're given some graph, and we want to find a subset of the vertices, subset of these vertices, such that no vertices share an edge. No vertices in our subset share an edge. So this one and this one could not be in the same subset because they share an edge. So we want to come up with some subset that does that. All right. So the way we can think of this is that we want to think of none of the vertices as being adjacent. So we want none of them are adjacent, and so we call them independent of each other. I'll give you an example of a way that we could solve this. If we have these ones selected as blue, you can see that none of them are their neighbors, and that is a perfectly fine solution. All right, so that's a problem one. It's a fairly simple problem. Problem two, oh my God, is vertex covering, where similarly we start with a graph. I don't know why these aren't showing up. Oh my God. So we start with a subset of vertices, and we want to determine that our subset, which are these right here, are connected to every single edge. So every single edge is connected to one of the nodes or one of the vertices in our subset. So if we have these ones right here, this is a potential solution for it. We see that every single edge shares a connection with one of our nodes in our subset. All right. So the question is, what is the relationship between vertex cover and independent set? So I'm going to show you right here. So we want to prove that independent set reduces to vertex cover, right? So look at this right here, and I would like to take some time, and I want someone to try to come up with a way that we could do the reduction. It is also a slightly harder problem than the first one, but is much simpler than the 3-sat reduction we did. So give it a go. Pull out a pencil and paper and try it. It's actually, doing these reductions is surprisingly fun once you get into it, because you have to think about the similarities between these problems in sort of abstract terms, and then you get to be a little bit clever in finding out how to do the reductions. So I say give it a go. If anyone has any ideas or just notices anything about these problems, share it in chat or shout. I think there is, yeah.
So just from the visual that you gave us, I'm not 100% sure how general this is, and I get the impression that it's not the case. But if we were to first solve the independent set problem, right, which would be get all of those blue nodes, and then just simply look at take every node that's not in that set. From this picture, that would yield a solution to the vertex cover problem. So if you just first solve the independent set, and then you just take everything that's not in that set.
So
specific example, that would be a solution to the vertex cover problem. I'm not convinced it generalizes very well, but that might be something to work with.
I'll give you two things. So first off, like I said, it is inevitable to happen, but you actually have the reduction backwards. So we need to solve the vertex problem covered first, and then So we're converting the problem. So we are converting this problem into this problem. But like to get our solution to this problem, we're solving this one first and then using that solution. So yeah.
I thought we were
we
just
can-
assuming that we had like some solution to the vertex for a problem.
The second bit, right, is that you're actually right. So that relationship, this like not relationship here is a good thing to notice. Since we are just out of time, like right about now, I'm going to say that each of you should take like the rest of class. Oh, someone actually put it in here. So basically, Bailey did get essentially the correct solution, and is like attempting to prove exactly what you just said, which is the fact that these are disjoint sets. The independent set that we find is going to be absolutely disjoint with our vertex cover that we find, and you actually know that they will sum up to all of the nodes in our, or all the vertices in our vertices set. So that's yeah. I can read through it, but all of you guys can read through that. So I want you to try to convince yourself of that fact, and try to see, like, you know, how you would formulate it if you wanted to try to convince someone of this fact, and see if you're able to do it. I think it's an interesting thing, and it's a little bit fun to do, so I recommend taking the time to do it. I'm going to use the last 2 minutes here to answer any more questions that anyone has about all of this material. I know it's quite a bit of material, but hopefully it landed for the most part. I know I had some missing animations, but I think hopefully that didn't mess up too much. So anyone have any questions they want to ask about it?
You may have already talked about this because I had to run out for a sec. But do we know what the complexity of proving P versus NP is? Like, that's a problem in and of itself. Does it have its own complexity?
I don't think we assign any complexity to it. There might be a paper out there trying to do that, but I think it's something that, you know, we can't really analyze the complexity of too well. This actually brings up kind of an interesting point, which is like human like problems that humans tackle with their brain and like their behavior. How do we classify that complexity? And that is an interesting and pretty open question. I think in general, I think people and the theory people in CS like to formulate these only as like these nice algorithmic problems and don't really try to apply that too much to like real world messy things. But I'm sure people have tried. I don't think there's any agreed upon decision there though. As Hava, if you know anything more about that, I don't really know anything.
Because I'm thinking, like, in theory, could there potentially be some algorithmic way of proving it one way or another? Like you were saying, you take essentially a whole bunch of problems in one class, and you identify like key properties of those problems that put them in that class, and then you identify like key properties of problems in the other classes, and you just sort of iterate. I know this is very vague, but like iterate through all of the problems and show equivalence of those properties or something like that.
So you are sort of hitting on something that is a little bit more more theoretically heavy.
What's the goal in doing that? What do you think it will buy for you?
Like I said, I'm like a brute force way of proving whether or not P is equal to NP.
What do you mean going on all over the problems? I mean, there are unbounded many.
P and NP, yeah, I guess that's the only thing is like, yeah, there's an unbounded amount of them. But maybe if we got like enough examples, we couldn't be conclusively sure, but maybe we could increase confidence.
No, that's the point. I mean, that's the point. I mean, up to some approximation, there are many answers. The question is really just the ultimate answer.
Okay, gotcha.
I think something kind of worth noting that is tangential, sort of, is this idea that, and you would see this more in 501 if you end up taking it, is this sort of idea that if there is a solution, so if it is possible to find a solution to P versus NP, then there is some logical like statement that would get you there. And like doing that has some sort of complexity, and there is like a lot of complexity classes are actually based off of this this lower order or high order logic. And you can, it's a little bit more complicated than that though, but I think it's not really worth getting into. But there is people thinking about that sort of thing, and you can learn more about it in 501. All right, cool. Anyone else have any other questions? It is
something about the test for Friday.
Yeah. So you want to talk about the test?
No, just repeat, the basics.
Okay. Yeah. Yeah. Test is on Friday, 2 days from now, during the discussion period, and we did allow an online book in the exam 1, but I want to remind all of you that we are not allowing online book for exam 2. All right. So that is this next one on Friday. You cannot have your book online. Only handwritten notes or physical pages. If you want to have information from the book and feel like it is unfair to not be able to use the online book, I would recommend that you either print off the pages that you want to use, although I would recommend you don't use too many of the pages. And a better solution would be to write down your notes of all of the information that you want to have from the book on hand, and do it as as small as you can, because you don't want to have this massive stack of pages that you're shifting throughout the entire exam. I think, weirdly enough, I do truly believe that not having the online book will probably be beneficial to some of you. I know it might not feel that way, but there's a lot of like wasted time and a lot of like confusing yourself by looking at the book. Yeah. All right. I think someone, or Bailey was asking about the time. I don't remember the exact time off the top of my head. I know it's during the discussion period. Hava, do you remember the time?
Well, I think 9:30.
9:30?
I think.
So you think, all right, well,
In Piazza.
it says on Piazza here. I can check
Yeah, I
Piazza.
know that in the morning we have one test for people from abroad. So we have a
9:30
bunch of options.
9:30 to 11 EST. All right. Cool. I'll stop sharing now. All right.
Okay.
Yeah. I guess I will stick around for a little bit in case people have questions, but otherwise you're free to go, or you were a minute ago, so 4 minutes ago.
Awesome class and most beautiful slides I've ever seen.
I was like genuinely very upset when I had the animations not working, because I just went through it and like double checked like on the slides, and I was like, okay, seems good, and then I didn't check those few apparently.
It's really beautiful. Like the
I really like this style. Like the on Google Slides, it lets you like pick the background color, and I picked that one, and I put some like pastel colors on.
Wonderful, because you chose like the word, like, and then the parentheses were the same, like the word, and then size was size, and it's like, yeah, it was amazing.
Thanks. Yeah, I genuinely like making these slideshows, which maybe is pretty nerdy, but I do like it.
Yeah. No, it's beautiful.
I guess if any of the
people I think that we're going to meet sometimes later.
Okay.
Do you have more things, or why don't I let you off and we'll tell everybody to meet at 4:30 maybe, or what's your?
I have my club is at 6. And then I have my homework due tomorrow. That I still need to do.
Okay, so I'll try to finalize with the other.
Okay, yeah.
Okay.
Sorry, quick question, Hava. Do you still have your office hours later today?
I forgot about it. I can have some if you want.
Yeah, I did want to. I had some like logistics questions that I wanted to ask you at some point.
Okay, sure. Something like 4:30.
Yeah, that should be fine.
Okay.
All right, cool. So I'll just go to your the normal Zoom room around 4:30 then.
Okay, bye-bye.
All right, cool. Thanks.
William, did you have something you wanted to ask too while we're here?
Oh, no, I was just, no, I had nothing to ask. I just hadn't left yet.
Okay, yeah. Well, I guess we should get going then.
Cool.
All right.
Oh, thank you. Bye-bye. I'll send you the recording. Bye-bye.
Yeah, thank you. Bye.